Here's a scenario. You're building a food delivery app. A user places an order, your backend needs to do 5 things. Save the order to the database, notify the restaurant, assign a delivery partner, send an SMS to the user, and update the inventory. If you do all of this synchronously in a single API call in sequence, your user is staring at a loading screen for 4 to 5 seconds. That's a broken experience. Now, what if I told you that with one architectural decision, you can make your API respond in under 50 milliseconds, handle all 5 of those tasks in parallel, and never drop a single event even if one of your downstream services crashes? That decision is a message queue. Today, we are building one from scratch.
Before we jump into the design, let's understand exactly what breaks when you don't have a queue. In a tightly coupled synchronous system, service A calls service B directly. Over HTTP or gRPC, service B calls service C calls service D. This creates 3 specific problems. Problem 1. Availability coupling. If service B goes down, a crash, a deployment, a timeout, service A fails too. Your user gets a 500 error because of a downstream problem that has nothing to do with their request. The failure propagates upward. Problem 2. Speed coupling. Your system is only as fast as your slowest service. If the SMS provider takes 2 seconds to respond, your user waits for 2 seconds, even though saving the order to your database took 5 milliseconds. Problem 3. Scalability coupling. Traffic spikes. Your order service is suddenly handling 10x load. Every one of those requests is hammering the notification service directly. The notification service gets crushed. Everything backs up. Pause. A message queue solves all 3. Instead of calling service B directly, service A drops a message into a queue and immediately returns a response to the user. Service B picks it up whenever it is ready. The 2 services are completely independent in time, in speed, and in availability. This is called temporal decoupling. It's the core idea behind every message queue ever built. Now, let's get precise with the vocabulary because interviews will test you on these exact terms.
Producer, the service that creates and sends messages. In our example, the order service is the producer. It puts an order-placed event into the queue. Consumer, the service that reads and processes messages. The notification service, the restaurant service, the inventory service, all consumers. Each does its job independently. Broker, the server that sits in the middle. It receives messages from producers, stores them durably, and delivers them to consumers. When people say Kafka cluster or RabbitMQ node, that's the broker. Message, the unit of data moving through the system. It has a key, a value, the actual payload, typically JSON or binary, and metadata like a timestamp and an offset. Topic, a named category or channel. Order placed is a topic. Payment processed is another topic. Producers publish to topics. Consumers subscribe to topics. Think of topics as the table of contents for your event stream. Now, there is an important architectural distinction you'll get asked about in interviews. Queue model versus pub-sub model. In the queue model, also called point-to-point, each message is consumed by exactly one consumer. You have 10 worker instances and 100 tasks. Each task goes to one worker and one worker only. This is great for task processing, job queues, work distribution. In the pub-sub model, publish-subscribe, each message is delivered to all subscribers. When a payment is completed, the notification service gets it, the analytics pipeline gets it, and the fraud detection service gets it. All 3 independently. One event fans out to many consumers. Real-world systems like Kafka support both models using a mechanism called consumer groups, which we'll get to in a few minutes. Now the critical question. How do you make a queue scale to millions of events per second?
Here's the bottleneck with a single queue. One machine can only handle so many writes per second, so many reads per second. You hit a ceiling fast. The solution is partitioning. A topic is split into multiple partitions. Each partition is an append-only log. Messages are written to the end sequentially, one after another. No random writes. Each message is assigned a unique sequential number within its partition, called an offset. Why is append only significant? Because sequential disk writes are orders of magnitude faster than random writes. This is one of the architectural decisions that makes Kafka capable of writing over 1 million messages per second on commodity hardware. Now, partitions can live on different broker machines. 12 partitions across 4 brokers gives you 4x the write throughput of a single machine. You scale horizontally by adding brokers and redistributing partitions. How does a producer decide which partition to write to? 3 strategies. 1. Round robin. Distribute messages evenly across all partitions. Good for load balancing when message order doesn't matter. 2. Key-based hashing. Hash the message key to determine the partition. If you always want all events for a specific user ID to land in the same partition, use user ID as the key. 3. Custom partitioner. Write your own routing logic. Why does key-based routing matter? Ordering. Messages within a single partition are strictly ordered by offset. Messages across different partitions have no ordering guarantee. So if you need all events for a particular user to be processed in the correct sequence, hash by user ID. Every event for that user lands in partition 4, in order every time. This is a classic interview trade-off you should be able to articulate. More parallelism versus stricter ordering. More partitions means more throughput, fewer partitions means stronger ordering guarantees. You cannot have both at maximum.
Partitions scale writes. Consumer groups scale reads. A consumer group is a set of consumer instances that jointly consume a topic. The rule is each partition is assigned to exactly one consumer within the group at any given time. 6 partitions, 3 consumers. Each consumer handles 2 partitions. 9 partitions, 3 consumers, 3 partitions each. It distributes automatically. What happens if a consumer crashes? The broker detects it, triggers a rebalance, and redistributes its partitions to the surviving consumers. The system continues processing with no manual intervention. What if you have more consumers than partitions? The extra consumers sit idle. They are on standby. This is why partition count matters. It's your ceiling for parallelism. You can't have more active consumers per group than you have partitions. Plan your partition count at design time. Reducing partitions later is painful. Now here's where consumer groups unlock the pub sub model. If you have 2 separate consumer groups, say notification service group and analytics service group, both subscribe to the same payment completed topic. Each group gets its own independent copy of every message. The notification service processes the payment event and sends the SMS. The analytics pipeline processes the same event and updates the revenue dashboard. Neither knows the other exists. Neither blocks the other. And critically, each consumer group tracks its own offset independently. If the analytics pipeline falls behind during a traffic spike, it does not affect the notification service at all. They are completely decoupled in their consumption rate.
Partitions give us scale. Replication gives us durability. Every partition has one leader and one or more followers, also called replicas. In production, the standard replication factor is 3. Your data lives on 3 separate physical machines simultaneously. All writes go to the leader. The leader appends the message to its log. Followers continuously pull from the leader to replicate the data. Now a broker goes down. The leader partition is gone. What happens? A coordination layer. In modern Kafka, this is K-raft, a raft-based consensus mechanism built into Kafka itself, replacing the older zookeeper dependency. Detects the failure and promotes a follower to the new leader. Producers and consumers seamlessly redirect to the new leader. No manual intervention. But there's a nuance. Which follower gets promoted? Only followers in the ISR, in-sync replicas list. A follower is in sync if it's not too far behind the leader. If a follower is lagging, say its network connection was flaky and it missed the last 500 messages, it is removed from the ISR. It will not be promoted. This prevents stale data from being served as the source of truth. Producer acknowledgement modes. This is a classic interview question. ACK is equal to 0. Fire and forget. The producer sends the message and doesn't wait for any acknowledgement. Maximum throughput, 0 durability guarantee. If the broker crashes mid-write, the message is gone. ACK is equal to 1. The producer waits for the leader to acknowledge. The leader writes to disk and sends the ACK.
If the leader crashes before the followers have replicated, you lose that message. ACK is equal to all. The producer waits for all in-sync replicas to acknowledge. Zero data loss guarantee. Slower because you're waiting for multiple machines to confirm the write. The choice maps directly to your use case. Payments, inventory, financial events, ACK is equal to all. Real-time analytics where losing 0.01% of events is acceptable, ACK is equal to 1. Non-critical metrics, ACK is equal to 0. This is the core trade-off of replication. Durability versus write latency. Stronger guarantees cost you time.
This section is what separates a good candidate from a strong one in a system design interview. Delivery semantics. At most once. Send the message once. If delivery fails, do not retry. The message may be lost, but it will never be processed twice. How it works in practice? The consumer reads the message from the queue and immediately commits its offset before it actually processes the message. If the consumer crashes mid-processing, the message is marked as consumed and will not be redelivered. Use this for non-critical high-frequency data, analytics events, live metrics dashboards, scenarios where losing a small percentage of events is acceptable and duplicates would cause more harm than losses. At least once. The consumer processes the message and then commits the offset only after successful processing. If the consumer crashes before committing, the broker redelivers the message. This guarantees zero message loss. The consequence? You may process the same message more than once. A consumer crash between processing and committing the offset results in a redelivery. This is the default in most production systems. Order processing, email notifications, payment events. The catch? Your consumer must be idempotent. Processing the same message twice must produce the same result as processing it once. You achieve idempotency by checking a unique message ID against a deduplication table before processing. If the ID already exists in the table, skip it. If not, process it and insert the ID. Upserts instead of inserts in your database. Deterministic output keys. Exactly once. The holy grail. Every message is processed exactly once. No loss, no duplicates. The problem? It's complex and expensive. In Kafka, this requires the transactional API, coordinated atomic writes across the producer, broker, and consumer. If any part of the transaction fails, the entire operation rolls back. Use it only when the cost of duplicates is unacceptable and the business justifies the overhead. Financial transactions, inventory deductions, ledger entries. The practical reality? At least once delivery with idempotent consumers gives you the same effective guarantee at significantly lower operational complexity and cost. Most engineers choose this path.
What happens when a consumer cannot process a specific message? The message is malformed. The data schema is invalid. There's a bug in the consumer logic. The consumer throws an exception, rolls back, and the message gets redelivered. And it fails again, and again, and again. This is called a poison message. Without handling it explicitly, it blocks your queue indefinitely. Messages stack up behind it. Your consumer is stuck in an infinite retry loop on a single bad event. A dead letter queue solves this. After a configurable number of retry attempts, say 3, the message is automatically moved to a separate dedicated DLQ topic. Your main queue unblocks immediately. The rest of your events flow normally. The DLQ gives you two things. First, operational continuity. Bad messages never block good ones. Second, an audit trail. Every failed message is captured, timestamped, and available for investigation. In production, you always monitor your DLQ size and set up alerts. If messages start accumulating there, it means either your consumer has a bug or something changed in the upstream data schema. Retry strategies. How you retry before sending to the DLQ matters. Linear retry. Retry every n seconds. Simple. Works for transient failures. But if you have 100 consumers all retrying every 5 seconds simultaneously, you create a thundering herd that hammers your database. Exponential backoff. First retry after 1 second. Second retry after 2 seconds. Third after 4 seconds. Reduces hammering. Standard approach. Exponential backoff with jitter. Add a random offset to the backoff time.
So instead of all consumers retrying at exactly the 4-second mark, they spread across a window. This prevents synchronized spikes and is the industry standard approach for distributed systems.
What happens when producers are significantly faster than consumers? Traffic spike. Millions of events per second coming in. Consumers processing at their normal rate. The queue grows, memory fills up, disk fills up, broker falls over. This is the backpressure problem. 3 strategies to handle it. Consumer auto-scaling. Monitor consumer lag, the gap between the latest message written and the latest message consumed. When lag exceeds a threshold, trigger horizontal scaling. Spin up more consumer instances. Kubernetes HPA with a custom metric on consumer lag handles this automatically. Producer throttling. The broker explicitly signals producers to slow down when it's under load. You can configure rate limits on the producer side so no single producer can flood the system. Retention policies. Don't hold messages forever. Configure time-based retention. Delete events older than 7 days. Or size-based retention. Max 1 TB per partition. Oldest messages purged first. Combined with consumer lag monitoring, this gives you a safety valve. Consumer lag is your primary health metric for a message queue in production. If lag is flat, system is healthy. If lag is growing, you have a problem. Scale your consumers before it becomes an outage.
Let's put everything together into one coherent design. Left side, producers. Multiple services published to different topics. The order service writes to order placed. The payment service writes to payment completed. Each producer is configured with the appropriate acknowledgement mode for its data criticality. Center, broker cluster. 3 brokers. Topics divided into 6 partitions each, distributed across the brokers. Each partition has a leader on one broker and replicas on the other 2. This gives us both horizontal scale and fault tolerance simultaneously. Above the cluster, coordination layer. K-Raft manages cluster metadata. Who is the leader for each partition, the ISR lists, consumer group offsets. This is the brain of the cluster. Right side, consumer groups. 3 independent consumer groups: the notification service, the analytics pipeline, and the fraud detection service. Each group has multiple instances. Each instance is assigned partitions from its group's offset position. Below, dead letter queue. A dedicated DLQ topic for every consumer group. Failed messages after 3 retries route here automatically. Monitoring alerts fire when DLQ size crosses a threshold. Top, observability layer. Producer throughput, broker disk usage, consumer lag per group, DLQ size per service. These are your 4 dashboard panels for operating this system. That is your complete distributed message queue design.
Real-world choice comes down to 3 main options. Apache Kafka, log-based append-only storage. High throughput, handles over 1 million messages per second on a single cluster. Messages are retained for a configurable period, enabling message replay. Consumer groups enable parallel processing at scale. This is the backbone of event streaming at companies like LinkedIn, Uber, and Netflix. Choose Kafka when throughput exceeds 100,000 messages per second, when you need event replay, or when you're building a microservice event bus. RabbitMQ, traditional message broker. Rich, flexible routing through a concept called exchanges and bindings. You can route messages based on content, headers, wildcards. Lower latency for smaller volumes. Better for RPC-style request-reply patterns and complex routing logic. Choose RabbitMQ when your throughput is moderate, and routing flexibility matters more than raw scale. AWS SQS, fully managed, 0 operational overhead. You don't manage brokers, you don't manage replication, you don't manage availability zones. AWS handles all of it. Standard queues for high throughput, FIFO queues for ordered processing. The right choice when you're already on AWS and operational simplicity is the priority. One-line decision guide. Event streaming at scale, Kafka. Simple, reliable task queue with no infra management, SQS. Complex routing logic at moderate volume, RabbitMQ.
Before you close this video, here's your interview checklist. Clarify requirements first. Is this a task queue or an event stream? Do they need message replay? What's the expected throughput? What are the latency requirements? Ask before you draw anything.
State your delivery semantics explicitly. Don't say reliable. Say at least once delivery with idempotent consumers. Always pair partitions with replication. Partitions give you scalability. Replication gives you durability. You need both in any serious design. Add a dead letter queue. This is a signal of production maturity. Interviewers notice when you include failure handling for poison messages. Talk about monitoring, consumer lag, broker health, DLQ size. This shows you've thought about operating the system, not just building it. Know your trade-offs by heart. More replicas equals stronger durability equals higher write latency. More partitions equals more parallelism equals weaker global ordering. Exactly one semantics equals strongest guarantee equals highest complexity. Trade-off fluency is what separates senior engineers. Message queues show up everywhere in modern backend architecture. Payment systems, notification pipelines, video processing, order management, real-time analytics. You will design this in almost every product company interview. If this video was useful, like it, subscribe and hit the bell. Next video we go deeper on Kafka internals, how log segments work, log compaction, and the zero copy read optimization that makes Kafka genuinely fast at the OS level. See you there.